Today we're looking at mechanical energy conversions. At this point, we have learned about work being a force applied over some displacement. We've looked at power, which is the rate at which work is done. And we've learned about energy, and energy, of course, being the ability for something to do work. In other words, apply a force over some displacement. But today we're looking at energy conversions, and that's how we can use the types of energies we've learned about to calculate either a height or a speed without having to worry about the kinematics, the exact acceleration at different points. A good example of when this could be used is when we have non-constant acceleration. So in kinematics, we learned that velocity, a new velocity, equals the initial velocity plus acceleration times time. But that works really well when acceleration is a constant number. But what happens when it's not? In other words, like, what if we had a slide that had bumps in it, or a ramp that was curved, or a spring that was releasing? All those things produce non-constant acceleration, and it makes the math very difficult if we're using kinematics, which is why we study energy. Energy makes this much, much easier to calculate. Let's start with a little bit of review. We want to calculate the gravitational potential energy of a 20 kilogram stone at rest on a 9-meter high hill. We know it's gravitational potential energy here because the energy is of position, right? It's of height, and gravitational potential energy is our energy of height. If we lifted it higher, we'd have a higher GPE. If it's lower, right, it would have less. So the first thing we need to do with this problem is, of course, write our formula. Make sure you always, always, always write the formula. Our potential energy formula is mass times gravity times height. You should have that written in your notes. Let's plug in the mass, gravity, and height. Then we'll just simply multiply, and we get 1800 joules. Remember, a joule is a Newton meter. Let's review kinetic energy. So here we're asked to calculate the kinetic energy of an arrow flying at 18 meters per second in Skyrim, the video game, because it is hard to get a picture of an arrow as it flies through the natural air. So we're looking for kinetic energy. Remember, kinetic energy is the energy of speed. The arrow is moving, therefore it has kinetic energy. How much? Let's write our formula. Remember, kinetic energy is 1/2 mv squared. Let's plug in our mass of 0.2 and our velocity of 18. And this is where it's very, very, very important. Order of operations. We square the 18 first before we do any of the multiplication. So some of the questions I've seen missed in the past, it's because people have not been doing their order of operations correctly. Always do your square before you do your multiplication. Then 324 times 0.1, we'll just move the decimal 1 to the left, and we get 32.4 joules. Now, let's see what happens when we drop something. When we drop a watermelon, for example, from a tower, because why not? What type of energy does a watermelon have in the beginning? Well, is it moving or is it high up? It's high up, so that is potential energy of gravity. If we let go of that watermelon, it will start to fall. That means as it falls, it's getting lower, which means it's losing gravitational potential energy, but it's also getting faster, which means it's gaining kinetic energy. So what we can say is the total amount of potential energy will eventually turn into the total amount of kinetic energy. As it falls, the potential energy turns into kinetic energy. Remember how we said that energy is conserved. We have the same amount of energy if there's no outside forces on our system. So the energy of one type equals the energy of the other type when the first is gone. In other words, when all the potential energy is lost, meaning it is no longer above the ground at all of that potential energy will now be kinetic energy. In the same way, when it's not moving, when we're holding it at the top of the tower, there is no kinetic energy. It is all in the form of potential energy. So what we can do is we can say the amount of potential energy when we're holding it at the top of the tower, the positional energy, the height energy, will be equal to the amount of kinetic energy, which is the movement energy, the velocity or speed energy, when it reaches the ground. So all we have to do is say our potential energy is equal to our eventual kinetic energy. The potential energy in the beginning equals the kinetic energy at the end. So let's plug in, or let's write our formulas for each of these. Potential energy of gravity is mass times gravity times height. Our kinetic energy is 1/2 mass times velocity squared. Let's plug our values in so we know the first, mass doesn't matter, right? Look, the mass is on the left side and the right side of the equation, so we can cancel it out. Now let's plug in the remaining values. 50 meter high is h, gravity is always 10, and we're solving for velocity. First step, 10 times 50 is 500. Now we need to divide each side by 1/2. Remember that dividing by 1/2 is the same as multiplying by 2. And we'll get the square root of 1,000, which is, of course, 32-ish, 31.6 meters per second. Let's do another. A man goes down a 4-meter high water slide. Notice we have non-constant acceleration here, right? You can't get his acceleration on the way down because that ramp is curved. So energy is the perfect approach. So our first question is, what type of energy does the man start with? In the beginning, is he moving or is he high above the ground? He's high above the ground, right? Which means he starts with gravitational potential energy. As he goes down the slide, he loses that gravitational potential energy because he's getting closer to the ground, which means he's gaining kinetic energy. He's getting faster and faster. You can see him getting faster and faster. So we want to know how fast he's moving at the bottom of the slide. Basically, this is the same question we went over just a minute ago with a slightly different setup. So remember, our first step is to list our types of energy. Gravitational potential energy in the beginning, kinetic energy at the end. They are equal because all of the gravitational potential energy turns into kinetic energy. Next step, we write our formulas. Notice again that the mass cancels out. Mass doesn't matter here. Let's plug in our values. 10 for gravity, as always. The height here is 4 meters, and we're looking for velocity. 10 times 4 is 40, and then 40 times 2 is 80. The square root of 80 is about 9 meters per second. But what if we're talking the other direction? What if we have a car that's moving at 18 meters per second when it runs out of gas, and then it's got a hill ahead of it? Our question is, how far up the hill can it move? So again, let's start with our basic question. What type of energy are we starting with? Is it high off the ground in the beginning, or is it moving fast in the beginning? Or is it moving at all in the beginning? Well, it's moving. So it starts with kinetic energy. What type of energy is that becoming? If it goes up the hill, it's going to slow down and lose that kinetic energy, but it's getting higher off the ground, which means that it is gaining potential energy. So we'll set those equal to each other. Kinetic energy is turning into gravitational potential energy. Let's go ahead and write our equations. 1/2 mv squared for kinetic energy, mgh for potential energy. Once again, the mass will cancel out. So we have 1/2 v squared equals gravity times height. We know our initial velocity was 18 meters per second, and gravity is 10. Order of operations. The first thing we do is square the 18. We have to do that before any multiplication or division. So squaring the 18, we get 324. 1/2 times 324, half of 324 is 162. And then we'll divide both sides by 10, and we get 16.2 meters. Hopefully this is a good introduction to energy conversions. If you have questions, make sure you reach out.